Assalamu alaikum warahmatullahi wabarakatuh. Welcome back for the third lecture. In this lecture we will be starting with detection of AM signals. Detection is the process of recovering the message signal back from the received modulated signal. It is exact the opposite of modulation, and the device that performs detection is known as detector or demodulator. Now, types of AM detectors. AM detectors are of two types. One is square law detector and another is envelope detector. First of all, let us discuss the square law detector. The input AM wave is applied to the square law device that has a non-linear input output characteristic. This square law device produces a number of terms of different frequencies. These terms are then passed through a low pass filter which is centered or tuned around the message signal frequency, and hence the desired output is obtained. And to let you know that this square law detector is not in your syllabus, that is why a cross has been put over here. It is not in your syllabus, but for your information I have added it to this slide. Number second is envelope detector, which is in your syllabus. It is a very simple and efficient device which is used for the detection of narrowband AM. Narrowband AM signal is one in which the carrier frequency FC is much higher as compared to the bandwidth of the modulating signal. It produces an output that follows the envelope of input AM signal. It is used in all commercial AM radio receivers. The circuit diagram is shown as below. Here you can see we apply the AM wave over here. This is RS resistor, series resistor. This is the diode which is connected to it. This is the capacitor. This is the resistor, and the detected output is traced from here, these two terminals. Now the working operation of this block diagram is explained as below. The standard AM wave is applied at the input as shown over here. For every positive half of this input wave, the diode will be forward biased and will conduct. During this half, the capacitor will get charged up to the instantaneous value of input signal. Right? From this point, when a positive half of the AM wave applies, diode gets forward biased, capacitor gets charged, and in the negative half, the diode will be in the reverse bias and will not conduct. But in the negative half, the capacitor starts discharging through resistance R until next positive cycle comes up. Now the input signal becomes greater than the capacitor voltage. Only then the diode conducts. The time constant of such a circuit is tau equal to RC, that is the product of these two terms R and C. The waveforms are given below. This is your input wave that is applied across the diode for every positive half of the cycle, or for every signal which is greater than the previous. The diode is on and the capacitor gets charged. When the voltage is less than the previous voltage, it gets disconnected, that is diode is off, capacitor gets discharged, and by passing it through a band pass filter, or low pass filter, you will get an exact copy of the modulating signal or the message signal, which is shown here M of t. The capacitor gets discharged through resistance Rs, and the diode, it gets discharged through resistance R. So this capacitor is being charged through resistor Rs and diode, while as the same capacitor gets discharged through the resistance R. So the charging time constant RSC should be very small as compared to the carrier time period. So from this you can conclude that Rs multiplied by C should be very less than 1 divided by Fc. Also the discharging time constant should be so long that the capacitor discharges slowly and the wave M of t is obtained accurately. So 1 by Fc, it should be very less than Rc. You can see here this is Rs and this is simply R. Disadvantage of standard AM. Number first disadvantage is power wastage. almost 67% of the total power is wasted using double sideband full carrier, that is standard aim. Second drawback is bandwidth inefficient, it gets affected by noise. Advantages of standard aim: aim transmitters are less complex, aim receivers are simple, less complex, cost effective, can travel very long distances, that is, these signals can cover a very large area. Applications of AM: number one is radio broadcasting, and number second is picture transmission in TV systems. The next point in your syllabus is double sideband suppressed carrier. Here we have two sides, but the carrier is not present. The equation of the AM wave is given by Sam of t equal to a cos omega ct plus a into mu by 2 cos omega c plus omega mt plus a mu by 2 into cos omega c minus omega m into t. This is the equation you already studied in the previous lecture, lecture 2. From the above equation we can conclude that the standard AM has carrier, upper sideband and the lower sideband. Besides this, the amplitude and the carrier of the amplitude and carrier frequency of carrier part remains unchanged before and after modulation. Also, it does not contain any sort of information within it. Also, from the power calculation, it has been calculated that at 100% modulation, that is mu equal to 1, 67% of the total power required for transmission of the carrier. So, if the carrier signal is suppressed and only the sidebands are transmitted, the resulting signal obtained is known as double sideband suppressed carrier, DSBSC-AM. By doing this, at 100% modulation, we can save about 67% of the total power. Now, we will see the mathematical analysis. We know from frequency shifting theorem of Fourier transform, x of t is x of omega, e raised power j omega t into x of t is x of omega minus omega c, and e raised power minus j omega c into t, x of t is equal to x of omega plus omega c. Also, we know that from Euler's identity, cos omega ct can be written as 1/2 of e raised power j omega t plus e raised power minus j omega t. So, when we multiply these two terms, we get this thing. You already have done is in the previous lecture. Now, graphically, if this is our message signal on performing the Fourier transform, we get this as the frequency domain of corresponding message signal. This is the frequency domain representation of the carrier signal, and this is the frequency domain representation of double sideband suppressed carrier. Suppressed carrier here means that you don't have a heavy line, black line over here. It is just represented in dashes, which means a dashed line means the absence of carrier. Now the transmission bandwidth is upper sideband minus lower sideband, which is again equal to 2 times omega m. Next is generation of double sideband suppressed carrier signals. How these are generated? In general, a product modulator is used to generate the signals. A simple product modulator is shown in the figure below. This is the message signal and this is the carrier signal. It is being just applied to the product modulator, and the output is your double sideband suppressed carrier signals. Now there are two forms of a product modulator. One is linear modulator, another is non-linear. First of all, we will discuss linear. A linear modulator is a system whose gain or transfer function can be varied with time by applying time variant signal. For example, ring modulator, which is shown as below. This is the primary winding of this first transformer T1. This is the secondary winding of this first transformer. This is diode D1, this is D2, this is D3, this is D4. These are points A, B, C and D, and this is transformer T2, and the output of this transformer T2 you get a double sideband suppressed carrier signal. Now we will see the operation of this linear modulator, or we will see the operation of a ring modulator rather. For positive half of the positive half cycle of carrier, diode D1 and D2 will conduct, as they will be forward biased. Positive signal over here and a positive signal over here, which means diode D1 and D2 get forward biased. They will conduct Due to induction at the coils of T1 and T2, output is obtained. But for the negative half cycle, diode D3 and D4 will conduct, and again due to induction, output will be available. Second type of modulators are non-linear modulators. These non-linear modulators make use of non-linear devices such as diodes, transistors, FETs, which are connected in a balanced mode so as to suppress the carrier of each other. A balanced modulator is one such example of nonlinear modulator shown in the figure given below. This is at these two terminals of this transformer we apply the message signal. This is diode D1, this is diode D2. We have this carrier signal which is applied at the center tapered of this modulator. We have R and C on the upper side, R and C on the lower side. Now we will discuss the demodulation of double-sideband suppressor carrier signals. The demodulation of DSB-SC signals is done by coherent detection or synchronous detection. Number second is envelope detection after carrier reinsertion. In coherent detection, double-sideband suppressor carrier wave is applied to the product modulator, where it is multiplied by a locally generated carrier which is synchronized in both phase as well as frequency with the carrier that was used at the transmitter side. The figure is given here. This is the antenna. It starts receiving DSB-SC signals. You get a locally generated carrier signal. They give it to the multiplier, and the output of this multiplier is being fed to the low pass filter, which filters it out and gives us the message signal back. Now the output of this product modulator is applied to the low pass filter, which removes the unwanted frequencies, and we get the desired output, that is our message signal. Second method is envelope detection after carrier reinsertion. In this method, a carrier signal is reinserted with DSB-SC, so it becomes full standard AM. Next, this signal is demodulated using envelope detector as done in the previous method of AM detection. The third point is here, single sideband suppressed carrier. We know that transmission bandwidth of standard AM as well as DSB-SC modulated wave is 2s FM, that is 2 times the message signal bandwidth. Hence, in both the systems, one half of bandwidth is occupied by upper sideband and the other half is occupied by lower sideband. In other words, same amount of information is transmitted twice. Therefore, both these systems are bandwidth inefficient. Since same amount of information is carried by both the sidebands, that is upper sideband and the lower sideband, we can suppress one of the sidebands and will transmit only one sideband. Such type of modulation or system where carrier as well as one of the sidebands is suppressed is known as single sideband suppressed carrier. In SSB-SC, almost 83% of the total power is saved at 100% modulation. Also, the transmission bandwidth is reduced by half. By this, we can accommodate twice the number of channels or users as compared to DSB-SC and DSB-FC. This is the Fourier transform message signal. This is your DSB-SC system representation. This is the single sideband suppressed carrier system where only upper sideband is transmitted. In this figure gives us the single sideband suppressed carrier where only lower sideband is being transmitted. Now, generation of SSB-SC signals. These are done by two methods. One is FDM, that is filter method, and the second is PDM or phase shift method. Frequency discrimination method. This method is used for the generation of single sideband suppressed carrier modulated signals if the message signal M of t satisfies the following condition. Message signal should not have any low frequency component, that is, frequency component in the range 0 to 300 Hz must be absent. The highest frequency component of message signal should be much smaller than the carrier frequency FC. In this method, we first generate a double sideband suppressed carrier signal with the help of a product modulator. From this DSB-SC, one of the sidebands is suppressed with the help of bandpass filter. The block diagram is shown as below. Now, the critical point in this method is the design of bandpass filter. This bandpass filter must have some frequency range so that the desired SSBSC modulated wave is obtained. Now the advantage and disadvantage, you can see it over here. We will go to the phase discrimination method. Block diagram is shown as below. We have the message signal which is applied to audio amplifier. Audio amplifier is given phase shift of 90 degree and then to the product modulator. At the same time, the audio amplifier is given, on the other hand, directed to the product modulator, and the carrier signal is given 90 degree out of phase shift to that one in which linear message signal is given, and vice versa over here. Then we have an adder which adds these two signals and the output is obtained as SSBSC. You can see the mathematical analysis here. Let the carrier signal be represented by sin omega t and the message signal be represented by sin omega m. So the input to the product modulator 1, that is the upper one, will be sin omega m t and sin omega c t plus 90, because carrier is being fed 90 degree out of phase to that one. And the output of product modulator 1 will be, according to this equation, sin A into sin B, which is equal to cos A minus B plus cos A plus B. So V1 will be equal to cos of omega c minus omega m into t plus 90 degree minus cos of omega c plus omega m into t plus 90 degree. Similarly, the input to the product modulator 2 will be sin omega mt plus 90 and sin omega ct, wherein the message signal is being fed out of phase by 90 degree. So applying the same formula, sin A sin B, we get V2 equal to cos omega c minus omega m into t minus 90 degree plus cos omega c plus omega m into t plus 90 degree. Adding these two equations, because we have an adder over here, adding these two equations we have 2 times cos omega c plus omega m into t plus 90 degree, which is your required expression. Advantages, disadvantages, you can see over here. Demodulation of SSBSC signals. The demodulation of SSBSC signals is done with the help of the synchronous detector, which is shown as below. Synchronous detector, you have SSBSC signal, you have cos omega ct which is locally generated. Both of these are being fed to the multiplier, which gives your signal ED. Then the ED is passed through low pass filter and your message signal is obtained. This ED is equal to SSB signal multiplied by local carrier signal. Both of these are being multiplied by the Hilbert transform. The Hilbert transform means that if we apply Hilbert transform in any signal, that is x of t, that is every frequency component of that signal is being multiplied by minus pi by 2 or minus 90 degrees. So the mathematical analysis is shown. We get ED equal to 1 half of x of t into 1 plus cos twice omega ct plus minus 1 by 2 x of h into t, that is, this is the Hilbert transform component, into sin twice omega ct. This ED signal is then passed through low pass filter and the terms centered around twice omega c are filtered out. You get a clean output here, that is your message signal is traced back. Advantages of SSB, you can look through here. Disadvantages, you can look here. Applications of SSB. SSB is used in the applications where power saving and the bandwidth requirements are important. Application areas are land and air mobile communication, telemetry, mainly used in military communication, in navigation, etc. Most of these are point-to-point communication applications. Now, why, if bandwidth is less, power is less, then why SSB is not used for broadcasting? As SSB transmitter and receiver require an excellent frequency stability, so a small change in the frequency can result in huge degradation of the quality of signals. Number second, it's important to design a tunable receiver oscillator with very high frequency stability. Thank you. Any queries, you can call. Thank you so much.